We have an example problem here. Two loudspeakers are located 3.35 meters apart on an outdoor stage. A listener is 18.3 meters from one and 19.5 meters from the other. During the sound check, a signal generator drives the two speakers in phase with the same amplitude and frequency. The transmitted frequency is swept through the audible range, which is 20 hertz to 20 kilohertz. What is the lowest frequency that gives destructive interference at the listener's location? All right, so we have a speaker and a speaker. They are a distance of 3.35 meters apart. There's someone out here that is 18.3 meters away from one speaker and 19.5 meters away from another speaker. So one of these would be an X1. I'm going to call the longer one X1, the shorter one X2, because I know delta X is the absolute value of the difference. And by making the larger one bigger, I'm going to get a positive answer for delta X anyway. So 19.5 minus 18.3, delta X, we're getting 1.2 meters. What that means is the sound from the second speaker, the right speaker in my picture, is traveling 1.2 meters farther than the sound from the left speaker. So here they're changing frequencies between 20 hertz and 20,000 hertz, and we want to find the lowest frequency that gives destructive interference. It's driving the two speakers in phase with the same amplitude and frequency, so we can get this situation of perfect destructive interference. M can be 0, 1, 2, 3, so forth. Okay, frequency is not in our equation. We know delta X. M, well, we're going to have to determine what M value works for us. Wavelength and frequency are related. We know the speed of a wave is wavelength times frequency. So in place of wavelength, I'm going to put speed over frequency. So delta X is m plus 1/2 times speed over frequency. If I solve for frequency, because that's what we're essentially looking for, is a frequency, I will have m plus 1/2 times v over delta x. V is the speed of sound. It's the interference of the type of wave we're talking about. So we know the speed of sound. We want the smallest value of frequency. Since m is in the numerator and we have these allowed values of m starting at 0, the smallest frequency will correspond to the smallest possible m value. And so we will be putting in 0 for m. V, we're going to use 343 because that's the value we're given and told to use unless they tell us a temperature, which they have not. Delta x we already calculated to be 1.2 meters. So if I put this in, I get 142.9. We have essentially 3 sig figs here. The 20 to 20,000 is just a range. It's not giving us a specific number to work with, just a range to work within. So our sig figs are going to be based off of these earlier numbers. So we have 3 sig figs. So the lowest frequency that would result in destructive interference for this specific listener is 143 hertz. As the generator keeps sweeping through, we could put an M value of 1, and we would find that if M is 1, we get 429 hertz. That would be the next time there's destructive interference. We could keep going with M values, but of course we don't need to. It asks for just the lowest frequency that would give us destructive interference.